So yeah, it's a pleasure to give a talk at the Lennard-Jones Centre, but I also feel like it's a bit on the side of what you seem to be currently doing. I had a glance at the previous talk and they are quite interesting, but I still hope that the learning about the water dimer and what you were actually interested in our group could be of some interest to you. So obviously water dimer is like the simplest water cluster. It has been studied quite extensively because of its importance, relative importance in understanding the many-body interaction in liquid water. There's also some kind of interest, there's some clue that it may contribute to the Earth's energetic budget by being providing some absorption of radiation in its continuum band, but those are still continued studies. In our case, we were interested in more fundamental question about the specific system. And actually, our interest on the problem started about 2 years ago when one of our collaborators in China, actually this project is a collaboration between myself here in Rwanda, some group in France, in Germany, and also in China. So one of the collaborators in this project and a group in China a couple of years ago made this very nice instrument, the free electron laser. And the goal of that instrument was to be able to record to an unprecedented accuracy the infrared spectrum of various water cluster, protonated water cluster, and neutral water cluster as well. So they made this nice recording of the water dimer, what they believe is the water dimer. And also on the side, they made some quantum calculation, quantum chemical calculation to be able to understand what are the features that they're observing in this spectrum. And these are what is specified on the table on the right. So specifically, they found that this specific band around 3800 is linked to the asymmetric stretch of the water acceptor. So this specific molecule, the asymmetric stretch of the water here. The next band, that is the B band, was linked to the free OH stretch, that is the specific motion. And then the C and the D band, the belief for the C to be the symmetric stretch of the acceptor and the D to be the OH stretch of the water donor. So now they made this calculation, they have the experimental results, but they found that depending on the level of theory that they were using, whether it was CCSD, MPTO, they tried some crude 12-dimensional vibrational calculation, they found quite a different type of assignment. So they did not have a definite understanding and assignment of those peaks. And for those reasons, they contacted some of our collaborators to start looking a little bit more closely at this problem, with the expectation that if we do more accurate quantum dynamical simulation on this system, we can match better the experiments that they were observing. So that was the starting point of the project. So along the way, that is last year, another paper was published. And that paper, actually, the main result of the paper is that they measure some bands of the spectrum of the water trimer. And what they found is that along this region, that is at 3550, more or less, wave number, they observe some feature that was linked to the water trimer and not the water dimer. And actually, when you look into the literature and you look the past few years, the past 20 or 30 years, you realize that many different assignments of the water dimer have been done. And there were no actual definitive conclusions stating that, okay, this specific band that is observed in the OH stretch region belongs to the water dimer and correspond to this specific motion. For instance, you can see the work of Coker or Page, or even the work of Preble, which are a bit more older. They all have this specific assignment of the OH stretch that was about 3530, 3550. And that's actually precisely what the group in China was referring to or was using as a reference for its calculation. However, another set of results, specifically this work by Kuyanov and Fozument and co-worker, had a very different assignment. They did not record the specific feature that is observed in this region, but they observed a very different set of results. In fact, this year, a few months ago, Vogt and co-worker published some reduced dimensional vibrational calculation on the water dimer, still looking at the OH3H band region. And the kind of result and the kind of frequency that they're observing were more in agreement with the work of Kuyanov and not at all in agreement with the spectrum and the assignment that was done by the group in China. So at this stage, we decided to provide a definitive answer to this problem. And we wanted to be able to correctly identify the OH stretch band, that is looking at the 3500, 3800 region of the spectrum. But more than everything, we wanted to be able to explain what is the origin of the splittings that are observed here. Globally speaking, we know that is the antisymmetric stretch of the proton acceptor, water proton acceptor. But specifically, what transition do they represent? This is some of the questions we try to answer, and those are quite kind of fundamental questions. For this purpose, then, we had a specific approach. We want to use a fully quantum mechanical approach right from the start. That is, we used a very accurate potential energy surface and dipole moment surface of the system. They were obtained at the CCSD level of theory, which is of chemical accuracy and better. Then for the dynamics, the molecular dynamics, we still follow the full quantum mechanical road using a wave function approach. That is actually very optimal and cost-effective, and that approach is the MCTDH method. I'm going to give a very short and brief introduction about it in the next few slides. So later on, after running the propagation, we actually have enough data, information, and enough tools to actually be able to analyze precisely the spectrum and try to get a better insight into what is actually going on in this specific system. So that's more or less the goal that we had on this project, and that we are near the end at the present time. So first of all, I want to give a very rough introduction about that specific method that I'm using for the quantum dynamics. So the starting point for most problem relating to molecular Hamiltonian is the Hamiltonian, and you consider the motion of the electron and the nuclei taken all together, but then after you apply the Born-Oppenheimer approximation to facilitate the solution of the problem. Then at the next step, you try to solve the equation for the electron and to obtain a set of energy values. Those energy values already provide you enough information about the system, but then you can interpolate those data or extrapolate them towards what is known as the potential energy surface. And that potential energy surface is actually an input for the next stage of the problem, which is the solution of the motion of the nuclei. Here again, because we decide to follow full quantum mechanical road, our starting point is once again the Schrödinger equation. But instead of going with the time-independent solution, we go with the time-dependent Schrödinger equation. There are some reasons why this kind of approach is better for some type of problem compared to the time-independent, but I'm not going to go too much into those details. So the most basic way of trying to solve this Schrödinger equation is simply to write in the wave function as expressed in 3, that is expanded on a basis, where you have a set of basis function that we tend to call primitive basis function, which are independent of time. Those basis functions span the whole Hilbert space. And then this wave function ansatz, you can plug it into an equation, a Dirac-Frenkel variational principal equation that relates to the time-dependent Schrödinger equation. And after solving it, you can follow the evolution of the wave packet at every time step according to equation 5. However, if you pay attention to this equation 5, you realize that a problem may arise. The fact that we have to compute a very high dimensional integral as the one displayed here can become quite problematic. And concrete example can be seen here. If you take a random molecule and you have, if the molecule is nonlinear, 10⁻6 vibrational degrees of freedom, and if it's linear, 10⁻5, you realize that the type of problem that we have, the kind of matrix problem that we have, quickly becomes too expensive to do. If for a diatomic molecule, you simply have a 10×10 matrix that you can probably solve with pen and paper, that is an integral of a 10×10 matrix. Very quickly, when you reach methane, you have to deal with a matrix of 1 billion by 1 billion, which is already way too much for the capabilities of current computer. Note that the system that we have to deal with actually has 6 atoms. So it could be very expensive to try to solve this problem using the time-dependent Schrödinger equation directly. And this kind of problem is a very well-known problem in quantum dynamics, but also in other fields, and is the issue about the curse of dimensionality. The exponential cost when we try to add a system of high dimensional. That's one thing that prevents using this type of methods for traditional system that are of interest in condensed matter. However, this problem has been around for quite some time, and various people have started working out some solution. The crude approximation that could be done for this kind of problem is try to do a time-dependent arbitrary resolution of the problem. In this specific case, that is a mean field approximation. In this specific case, you simply write the wave function as a product of function as provided in equation 6. But in this case, you see that the function which are expressed here not only depends on position, but also depend on time. And each one of these functions, actually, you can expand them on that initial basis that is called a primitive, that we have before called primitive basis, with a set of coefficients that depend on time, that is, that evolve with time. And the function also is also going to evolve with time. So more or less, the idea is that the function that you are describing here is kind of following the motion of your wave function at every time step. Then again, if you apply a set of constraints, because this kind of expression is not unique, and you plug them into a variational principle, you get a set of propagation equations for the coefficient and the propagation equation for these functions that are following the motion of the system. This method is very nice and very cheap. That is, it kind of breaks down the cost of traditional calculation to something that's very simple. Unfortunately, it's a mean field approximation, and we all know that the problem of correlation is something that is very important, and that's definitely missing from this specific expression. So something better that has been proposed about a little more than 30 years ago is the multi-configuration time-dependent arbitrary method. So here in this case, the way we write the function is kind of similar to the way it was written in the case, in the standard case. The main difference is that instead of having n, big N here, function, we have a smaller number, at least a number that we expect or we want to be small, n, in which we expand the wave function. And we have this product of kind of arbitrary products that we are summing with a new set of coefficients. Now, the benefit that we are having is that those specific single particle functions that we have in the time-dependent arc, that is, that depend on the position, but also depend on the time, are used quite efficiently here. And again, they are expressed on the basis of time-independent function, where the coefficients here are going to change with time. So by using this kind of expansion, and again, plugging it in a variational principle using the constraint, we are actually adding correlation into the description of the system. In the end, we then get, after doing some algebra and some calculus, we get two sets of equations, one for the propagation of the coefficient that are used in the expansion, and the next for the propagation of the single particle function that is an optimized set of basis function. So this method is extremely efficient. And this can be verified if you compare the cost of the very first method that I present, the standard method, with this MCTDH method. If you assume that you took, for instance, 32 grid points, for the standard method and just need 7 optimized functions for the MCTDH method, you see that when you are dealing with a problem that has dimension 9, in the standard method, you need a petabyte of memory, while you need just an amount in gigabyte of memory. So the scaling is reduced quite significantly when you get to system of higher and higher dimension. So this is more or less the core idea about the MCTDH method. It's a method where you try to optimize the basis function that you use for the dynamics, and that allows you to save in cost and also allows you to stay in computational time most of the time. There are other methods that are derived from the same MCTDH method that are even more powerful, but I'm just going to stop here for this relatively basic introduction on the method that we are using. So the next stage now is that when we want to run the propagation, the first thing we need is actually preparing the initial wave function. That is when we want to obtain the spectrum, we want to know what is the state of the system initially before receiving the radiation. And to do those calculations, instead of doing a real-time propagation, we can do an imaginary time propagation. And with the imaginary time propagation, we have the system that is going to coalesce into the ground state quite naturally. And that is going to likely be our starting point for our simulation. So that's also one of the possibilities of these specific methods and the way it was implemented in the code that is actually open access developed in Heidelberg. Okay, so now in the specific case of interest of the water dimer, we have used these are the parameters of the basis that we are using. And if we were to go with the standard method, that is the very first that I described before, the type of problem that we'll have to deal with is the 10 to the power 15 times 10 to the power 15 matrices. Here, thanks to the fact that we are using an optimized basis of function, we just have to deal with a problem that is about 1 million by 1 million, which is much more tractable on computing resources that we have on hand. And that's the specific strength, like it's like 9 order of magnitude reduction in the cost of the simulation by this specific approach. Now, one thing that I didn't mention, and that is related to the fact that you have to deal with a multidimensional integral, is that one way of reducing the cost of those multidimensional integral, not just for the MCTDH method that I presented, but more generally in great problem related to quantum dynamics, is that the Hamiltonian that you have to deal with, you want to express it in a sum of product form. And the sum of product form is this one expressed in equation 17. When you expand your Hamiltonian as a product of lower dimensional Hamiltonian with a specific set of coefficients. In that way, when you have to perform multidimensional integral, you just have to perform several one-dimensional integral, which are significantly cheaper to do. So now you have to realize that the Hamiltonian is consists of the kinetic energy operator and the potential energy operator. For the kinetic energy operator, most of the time and quite often, you can have it in this specific sum of product form. For instance, if you use Cartesian coordinates, they are naturally in the sum of product form. However, because we are doing this specific type of dynamics, we try to avoid having extra or unnecessary degrees of freedom that are appearing in the problem. So we try to select a set of coordinates that are more appropriate to study the dynamics. An example is the one that is shown on the side, and that's the one that we actually use. So we combine a set of Jacobi and valence coordinates to create our Hamiltonian. And thankfully, there's a program that is available online freely that allows you, given that you have a specific set of coordinate system in mind, to produce the kinetic energy operator directly in that specific sum of product form that will be appropriate for the kind of dynamics that we're interested in. The main hurdle that we usually have when dealing with this problem is dealing with the potential. The potential is nothing but uncommon most of the time. And still we want to have it in this specific form because it will facilitate the dynamics and the dynamical study, the molecular dynamics that we are trying to follow. For systems that have a relatively small size, there are some codes that are already available that can allow you to transform the system in sum of product form quite easily. That is for a molecule with 4 or 5 atoms. These are available. For the case that we have on hand, there were no simple tools to make it possible. However, a few years ago, there was some new development in the field, and there was some possibility of transforming any potential in relatively convenient dimension into what is known as the canonical polyadic decomposition, combining with a Monte Carlo sampling of the data point. And that program is MCTD. So that program also is nowadays freely available in the MCTDH package. And that's a method that we use to be able to transform our potential into this specific sum of product form at a decent cost. An example of how well the program is performed is this comparison that you have on top here with the actual numerical potential, and below the fit that was done thanks to this program. Overall, the root mean square error of the fit was a little bit less than 100 wave number in the whole range of interest for this specific calculation, which is actually good enough for the kind of studies that we want to do. So as I said, the first thing we want to do when we want to do the propagation is we want to prepare the system in the initial state. So what we did is that having the potential that we fitted once more using the MCTDH method to run the dynamics, we tend to prepare the initial state and we tend to compute the vibrational state of the system and compare them with more reliable and more accurate calculation. That's what we did in this specific case. So as you see, there's some difference between the calculation that we did, which is basis 1 and basis 2, with other theoretical results, the one, for instance, from Carrington. These two were done using the same potential energy surface. And we see that we are a bit different, but that's not too drastic because the kind of difference that we're interested in, the kind of difference we are expecting to see will probably be of the order of tens of wave number. So overall, we find that we are already in the good region and the good bracket when we compare our simulation from density calculation and more accurate quantum dynamics simulation. Those are time-independent calculation with experimental data. So I can come a little bit, talk a little bit more about it because there is an additional difference between what we did and what was done in that specific work, but if there's time, I can mention it later on. So how do we get the absorption, the infrared spectrum of the system? The first point, like I said, is to prepare the initial wave packet, like in the lowest energy state of the system. That's what we had as a starting point. Then we apply the dipole moment on this initial wave function and then do a propagation. And from the autocorrelation, the Fourier transform of the autocorrelation function of the propagation, that's how we extract the absorption spectrum. Now we have to add the contribution for all the direction of the dipole moment, the X, the Y, and the Z direction to obtain the complete contribution of this system. So initially I mentioned the paper of Fourier-Kozument as the one that we are doing, we are using for comparison in our simulation. And you can see here the spectrum that we obtained from our simulation, and here the spectra that they obtained from experiments. So for instance, first of all, you see this very first band that is observed here, which is also present in this specific range. There is this small SA band that appears around 3650, and actually we have something similar in this region. But for now, you may believe that, okay, it's not exactly clear. We see some wiggles also around here. Is it not another band? We are going to show precisely what is going on in this region in the next slides. And then we have these other features that is here that correspond to the FD peak. And you have now two bands that should correspond to the AA band. In principle, there should be three, but for now you just see two, and we're going to talk a little bit about that also later. So once we do the propagation, we actually have a tool that allows us to know what is going on in this specific calculation, not just observe the spectrum, but precisely say what is going on here. And how do we do that? So the fact that we are using a wave function based approach, we can actually start creating artificial excitation on the system. And we can create, for instance, a kind of a donor bond OH stretch and try to see what is going to be the signature on the spectrum. So we create an artificial system with that specific stretch and try to run a propagation and see what kind of signature appears. And that's what we did. And using this type of tools for various motion of each of the water, we can observe, for instance, the signature, this specific peak at 3600 that comes mainly from the OH, the donor OH stretch. And we see also another smaller signature in this region around 3650. The same with the band that I told you about, 3650 wave number here, that is shown in blue, correspond to the symmetric stretch of the acceptor. So very precisely, we can confirm the assignment that was made by the group of Kuyanov and Prozument, and we can also confirm the assignment that was made from those reduced vibrational calculations that I've shown you before. So more or less, we can understand precisely everything that we're observing here and know that these specific portion are probably mainly just artificial artifacts, and know from our simulation and from those artificial excitation where all of this feature comes from. So at this point, we more or less understand one part of the problem. The next part of the problem, it's a little bit more trickier, and that is understanding the splitting that is observed in the asymmetric stretch of the water acceptor. So to get a better understanding of that specific part, we have to realize that if you remember this figure, that there's actually a very small splitting between the lowest energy states of the water dimer. And considering the temperature at which the experiments are done, the population, those states are likely to be populated to some extent by a wave function. So what we did is that we took two separate wave functions, the first and the third, that is the lowest one, and the second excited one, and try to run the propagation and try to observe the kind of spectrum we obtain in each case. So if we do the propagation in the first case, we obtain this one, which is a little bit more like this, but for a shorter propagation time. And if we do for the second excited state, you have something that is actually quite different from the one on top. But if you combine the two, and if you believe what I'm trying to tell you, you actually see that there is no longer just two structures, but there is a third structure that occurs here, and that seems to be linked now to the acceptor asymmetric stretch that we try to understand. So more or less, we can say that the contribution of the three peaks that we're observing, they don't come just from the lowest state of the ground state, but it comes from some excited ground state of the system. And that's the understanding that we have at this moment. But actually, the story is not complete, because most of the story that has been done on this specific case has been done in the rotational-less case, like assuming that the water molecule, the water dimer is not rotating. But actually, that is not true, because this system has been studied a lot and quite extensively. And if you look in the literature, there's actually a very different picture that is provided and proposed for this specific system. And that picture suggests that for each of these states, there's actually a contribution from rotationally excited state that you can identify by Ka equal 1 here or here, that actually contribute to the system. And specifically for this AA contribution, which is the asymmetric stretch we are interested in, you see that there should be a contribution from rotationally excited state, both on the initial state and the final state. Remember that obtaining those structures is actually an overlapping between two states on the ground and excited states. So the next stage of our calculation is actually try to probe this specific set of transition, because what we did so far, taking only into account the J equal to 0 state, is not providing a proper description of what is going on for the antisymmetric stretch, which is actually the second and the last part of our investigation of the system. And we are currently running those calculations for J equal to 1 to get a better picture of this set of three asymmetric stretch that you observe here. Unfortunately, those calculations are a bit more expensive than the original one, but still we can still run them using the MCTDH code, and very soon we are going to get a more clear picture of what is actually going on for this specific system. So to conclude, and what we do and what we did is trying to perform a fully quantum dynamical study of this water dynamic system using very accurate potential energy surface and dipole moment surface. The simulated spectrum, from the spectrum that we obtained from simulation, we can confirm the assignment that has been done from some of the previous work. We disprove some of the experimental data or assignment that were made in the past. But our goal actually is not just to stop at the water dimer. The tool that we have is powerful enough to deal with system in higher dimensionality. The main drawback in our approach and in our understanding on water cluster using a fully quantum mechanical description is actually having reliable potential energy surface in high dimension, hopefully in the sum of product form, to make the calculation possible. Like the tool we have is powerful enough, but the input data, that is the potential energy surface, is not always in the correct format to allow us to explore a little bit better all this set of other water cluster. So I would like to close by thanking some collaborators in Paris, Fabien and David in Heidelberg, Marcus Oriol, Hans Dieter, and people in China who provide the potential energy surface and did some experiment. And we also have some funding from a grant through EPFL and University of Mohammed VI. And that's all. I would like to thank you for your attention with some nice picture from Rwanda. So thanks.